We're starting section 4.3. We're talking about logarithms. The goals for this section are to understand what a logarithm is, to solve equations with logarithms, to graph log functions, and to apply the properties of logs. And so we want to start with the definition, and I'll give you an informal definition first, and then we'll work toward a more formal definition in just a minute. So what I want to say is that the logarithm is the inverse of an exponential. The logarithm is the inverse of an exponential. And this is a nice statement for us to make because it ties together ideas that we've been talking about in chapter 4. So specifically, we studied the inverse in section 4.1, and we studied exponentials in section 4.2, and now that allows us to talk about logarithms here in section 4.3. So the math is really building on itself, and we're really taking some ideas and putting them together. So in section 4.1, we learned that to get an inverse, we need to switch the input and the output. Let's write that down. To get the inverse, of any function, we switch x and y. So for example, if we start with the exponential function, two to the x is equal to y, then we can find its inverse function. In the previous sections, we would have written this as y equals 2 to the x. The fact that we switched the two sides shouldn't make any difference. So in order to get the inverse for this function, remember we just switch x and y. So let's write that. That gives us 2 to the y is equal to x. And now, remember the next step to find the inverse function is to solve for y. And the question is, how can we do this? We don't have an operation to bring the y down out of the exponent. And so what we're going to do is we're going to invent a new operation. We're going to invent a new operation, which might seem like a strange idea, but really it's one that you've been doing for as long as you've been studying math. After you learned how to add, you wanted to do the inverse operation, and so we invented a new operation. We called it subtraction. Or after you learned how to square a number, then we needed to do the opposite. We invented a new symbol called a square root. So now we need to invent a new symbol to represent the idea that we're doing the opposite of this exponential. The opposite of this exponential. And so here's what we're going to do. We're going to start with 2 to the y equals x, and then the new operation is going to be called log base 2. And we're going to do it to both sides to keep the equation balanced. And then this log base 2, and this base 2 in the exponential 2 to the y cancel. and we're left with y equals log base 2 of x. In other words, when we write log base 2 of x equals y, that's what we just finished with, what does that mean? All that means is this equivalent equation. 2 to the y equals x. 2 to the y is equal to x. And so then we can generalize a little bit from there. So we don't have to use a base 2. Let's talk about base a. And there are some restrictions on a, which we'll get to in just a minute, but we don't have to worry about that yet. So let's have the definition of a logarithm. The definition of a logarithm says the log base a of x is equal to y. Simply means the exponential that it came from. Can you see what it would be? If we compare the new statement with the previous statement, the only difference is the base 2 is replaced by an a. The base 2 in the log becomes the base 2 in the exponential. So we have base a raised to the y power equals x. And there you have it. So we should go ahead and we should talk about the values that a, y, and x can have. And so, and the same values that they have here for the logarithm are the same values they have here in the exponential. So we already know something about what these numbers can be in an exponential. So we can just transfer that over to the logarithm. So the base a is a positive number, and a is not equal to 1. A is between 0 and 1, or it's greater than 1. And then x is the output from the exponential. Now, I understand that's a little weird. Usually you think of x as the input to whatever function, but remember, we switched x and y. So now x is the output from the exponential. Do you remember what the graph of the exponential looks like? Something like that, where the outputs are all positive, where the output is always positive, so then x must be greater than 0. Y, the output from the logarithm, is the same as the input to the exponential. The input to the exponential is any real number. And it's worth repeating one more time. The log is the inverse of the exponential. The log is the inverse of the exponential. Okay, well, let's go ahead and try to evaluate some logarithms. And that might help us to get a better sense of it. It's a brand new operation. It's a tricky one. A lot of students have trouble with it at first, but with a little practice, I think we'll get good at it. So actually, I tell you what, let's do. Let's keep that definition in sight while we start this first example. So we want to evaluate the log base 3 of 9. What does that mean? Well, log base a of x equals y means y is the exponent on that base that makes the number x. In other words, we're looking for the exponent on 3 that makes 9. The exponent on 3 that we can apply to a 3 to make 9. Can you see what it is? Let me say it one more time. Let me actually write it out. We want to ask the question, 3 to what power makes 9? And of course, that's 3 to the second power. The second power is the answer. And so we'll have our answer as 2. And then we could even give a justification for that answer by rewriting the log as an exponential. So, of course, that's what we did in the definition. We can do that in each of these examples. The base 3 raised to the second power makes that number 9. Okay, you might pause the video and try to do B, C, or D. I will warn you that properties of exponents are going to be real important now to get these answers. Okay, in part B, we're asking the question, we're trying to find log base 7 of 1. So 7 to what power makes 1? Can you read my writing there? 7 to what power makes 1? And so that's 7 to the 0 power. 7 to the 0 power. We could actually put an arrow on both ends of that implication to say each equation implies the other. Okay, so we're getting a little practice now. Let's see here. What's the question, first of all, for part C? The question is 10 to what power makes 0.01? And again, property of exponents is the key. You might think of 0.01 as 1 over 100. So that's 1 over 10 squared, or that's 10 to the negative 2. 10 to the negative 2. The answer is negative 2. That's the exponent that we need to put on 10. 10 to the negative 2 is the same as 1 over 10 squared, which is the same as 1 over 100, or 0.01. Let's do one more. Five to what power makes the square root of 5? We've talked about this a little bit in the last two sections. We said that the square root of 5 is the same as 5 to the 1/2 power. So the exponent will be 1/2. The base 5 raised to the exponent 1/2 is the same as the square root of 5. Okay, let's extend this idea a little bit. What we want to do now in these next two examples is we just want to convert between logarithms and exponentials. We want to convert between logarithms and exponentials. So, so every log can be written as an exponential, every exponential as a logarithm. So let's start with example 2, log base r of s equals t. R is the base of the logarithm, so r is the base of the exponential. And then t is the exponent. R to the t gives us the argument s. S is called the argument of the logarithm. r is called the base of the logarithm. So there's our answer. There's our equivalent form. And we can do this one more time, going back the other way. Here in the exponential, the base is x. So over here in the logarithm, the base is x. Y is the exponent. That's the answer to the logarithm. It goes over on the other side of the equal sign. And so we have log base x of z is equal to y. That's enough for now. In the next video, we'll learn how to solve some basic logarithmic equations.